Hello, my name is John Coonrod. I am with Rogers Corporation and I am a technical marketing manager. Today I'm going to be talking about final plated finishes and how these final plated finishes can impact the RF performance of circuitry. So with that in mind, give me just a moment to load up my PowerPoint and we'll get started. So the agenda I plan on following is shown here. I'm going to first go through a quick overview of insertion loss, even though probably most people that's going to watch this understand it already. Probably still a good idea to go through the basics anyway. And then after that, I'm going to get into more details about the final plated finishes and how they affect insertion loss and actually phase response for that matter. And then finally, I'll give you and talk about some of the data that I've collected over the years with different studies and showing how different final plated finishes can impact RF performance. So to begin with, a quick overview of insertion loss. And again, as most of you probably know, insertion loss is made up of 4 different components. There's conductor loss, dielectric loss, radiation loss, and leakage loss. And for the presentation today, the data that I'm going to be sharing, radiation loss is either insignificant or it's been accounted for, let's say. So I'm not really going to talk about radiation loss today, and there's a lot of reasons behind that. Radiation loss is a pretty big topic, and there's a lot of different variables to it. So for now, we're going to ignore radiation loss and just focus on dielectric loss and conductor loss. Now, leakage loss is another item I'm going to ignore today. And again, the data I'm showing really has no issue with leakage loss. And as a general statement, the high frequency materials used in the printed circuit board industry typically do not have leakage loss. And that's because the volume resistivity is so extremely high with these materials. Now, if you're using a material that's a semiconductor grade material, then leakage loss could be more of an issue, or in some applications where you're at very high power, leakage loss gets to be more interesting. But again, for what we're looking at today, leakage loss is not really an issue, and the same with radiation loss. So I'm really going to focus on conductor loss and dielectric losses. And to give you a good overview of how these different loss components behave to add together to give you the total insertion loss, I'm showing a study I did a few years ago with the exact same material. All the material that was used here was RL4350B laminate. And what I did was make microstrip transmission line circuits on different thicknesses of this laminate. So it's the same laminate, same copper, same everything. The only difference is different thickness of substrates, and the conductor width for the microstrip transmission line was different widths to account for maintaining 50 ohm impedance. And what came out of that is something pretty dramatic for showing that a thinner circuit is dominated by the conductor loss effects, thicker circuit dominated by dielectric loss effects. So I'll step through this real quick. The middle chart, I'll start with that because it has the legend. And on the middle chart, the thick purple curve is the measured data, and that's going out to 20 gigahertz. And at 20 gigahertz for a 10 mil thick material, which is a 50 ohm microstrip transmission line based on 10 mil 4350B laminate, I get an insertion loss of 0.7 dB per inch at 20 gigahertz. And then the green curve, which is the model total loss, that is the model I'm using, and that should match the measured loss. And there's little differences here and there, but overall it matches pretty good, close enough for what we're doing for this example anyway. And then the other curves, the red curve is conductor loss, blue curve is dielectric loss, and that's showing you how much of conductor loss and how much dielectric loss are adding up to equal that total loss of the green curve. Now, when you look at the same type of testing and looking at the chart on the left, that is still the same material, same everything except thinner. Now, instead of being 10 mils thick like the middle chart, the left chart is actually 6.6 mils thick, so it's thinner. And to maintain thinner and to maintain the same 50 ohm impedance for a thinner substrate, I had to make a more narrow conductor, and a more narrow conductor means you have more conductor losses. Basically, you have the same amount of power on and less copper to support it. So because of that, you can see there's an increase in insertion loss. The overall insertion loss is increased, and you can see the reason it increases because the red curve actually increased, and the red curve is conductor losses. So as a general statement, thinner circuits are more dominated by the conductor effects than thicker circuits. And thicker circuits shown on the far right, that's a 30 mil thick substrate. Again, 50 ohms, which means it's got a much wider conductor. And now the conductor effects are less of an effect. And it's the dielectric losses that really come into play. That's the blue curve. So dielectric losses are normally related to dissipation factor. So if you have a 30 mil thick circuit that's shown on the right, and you want to improve the losses, what you would do is actually do something to impact the dielectric losses. So instead of using 4350B, which has very good dissipation factor, you may switch to RL3003, which has an extremely low dissipation factor, and that would improve the dielectric losses, and that would improve the overall losses more significantly. If you change something about the conductor for the 30 mil thick substrate, it wouldn't do much. If you change something about the conductor for the chart on the far left, the 6.6 mil thick substrate, okay, that's going to make a difference. And normally it's the copper surface roughness that is pretty impactful. So on the left, a thin circuit is going to respond to conductor effects much more than the thicker circuit. Now, just to drive that point home a little bit farther, this is another study that I did where I'm looking at the same material again, and this material is RL4003C laminate with the same copper, same everything, except different thicknesses. And now I'm comparing bare copper to ENIG. ENIG is electrous nickel, immersion gold. And this comparison is actually showing the effects of conductor loss and how it affects the insertion loss, because ENIG, electrous nickel immersion gold, is actually affecting the conductor loss of the component of insertion loss. And in the case of the thicker circuit, the 20 mil thick, that's the blue curve bare copper, red curve same circuit except with ENIG. There's a loss difference between the bare copper and the ENIG for a thicker circuit, 20 mils thick, of 0.21 dB per inch. If you do that same comparison on a thicker or a thinner circuit, then that's the green curve and the purple curve. There's a 0.38 dB per inch difference. So the thinner circuit made on 8 mil thick substrate actually has it actually is affected by the ENIG much more than the thicker circuit. And ENIG is affecting the conductor losses, so this just shows that a thinner circuit's more affected by differences in the conductor effects than a thicker circuit. Differences in the conductor effects here is ENIG is causing more conductor loss than the bare copper circuits. So I've been asked many times before in microstrip, why does these plated finishes cause differences to insertion loss? Because most of the fields for microstrip are between the signal plane and the ground plane, and these plated finishes do not interact at that interface. The plated finishes actually plate over the conductors, so the left edge of the conductor, the top and the right edge of the conductor get plated with the metal finish, but where the fields are between the signal plane and the ground plane, that's not affected by the final plated finish. But what the trick is, at the left edge and the right edge of the signal conductor, there is high current density, and it's an edge effect essentially, that the plated finish will affect the conductor losses at the edge of the conductor. So left and right edge in a cross-sectional view, that's going to be affected by the worse conductivity of the metal finishes being applied. Now in the case of grounded coplanar waveguide shown on the right, that's a little different because now you have fields on the coplanar layer, the top copper layer, this ground signal ground. You have coupled fields, and that's actually 4 different interfaces where this lossy metal can actually have an impact on the RF performance. So you have current density on those sidewalls, and as you plate a lossy metal on there, that's going to be affected much more than just the microstrip with the 2 edges. So to show this, I've done a study here, again, using RL4003C materials, and this time using the same thickness, 8 mils thick, using the same copper, the standard DD copper. Everything was the same except the design of the circuit. In this case, the chart on the left is a microstrip transmission line. The chart on the right is a grounded coplanar waveguide. Actually, it's tightly coupled grounded coplanar waveguide. And the comparisons I'm showing is the red curves are for bare copper, the blue curve is the same circuit except using ENIG plated finish. And ENIG, electrous nickel immersion gold, the nickel is about 1/4 the conductivity of copper. And because of that, it adds to the conductor losses. Also, nickel is ferromagnetic, and it does have some loss component related to the relative permeability. And anyway, so you can see a difference here between microstrip at 50 gigahertz. I see a difference between bare copper and ENIG of about 0.5 dB per inch difference, while that same material, but with a grounded coplanar waveguide design, the difference is about 1.2 dB per inch difference with a tightly coupled grounded coplanar waveguide. Again, red curve is bare copper, blue curve is with ENIG. Now, there's a lot of different metals used in the industry for printed circuit boards to do this metal finish. Probably the most common one would be ENIG, which I've been talking about, electrous nickel immersion gold. But there's also immersion tin. There's also solder, of course, immersion silver. There's also something called OSP, which I'm not going to talk much about today. But I'm showing some of the conductivity values here just to give you an idea of the differences in conductivity. And also I wanted to point out the skin depth formula. And what's interesting about this, it gives you a hint to why these different metals cause more losses due to being plated to the copper. And one reason is the conductivity will make a difference in skin depth. So it's kind of a double-edged sword in the case of ENIG, where nickel is less conductive by copper by about a quarter or so, pretty significant difference anyway. So a lower conductivity metal also causes a thicker skin depth. So not only does the less conductivity cause more conductor losses, now you're actually using, or I should say the RF current is using more of that lossy metal because you have a thicker skin depth. So these are kind of some of the things to think about. I did a study several years ago using the same test vehicle. It's a microstrip transmission line on a thin material, 5 mils thick with rolled copper. Rolled copper is very smooth. And because of that, you have very little conductor effects due to the copper itself. And here I'm showing some comparisons. Now the blue curves, I left them all some shade of blue to show that they really are behaving the same. The reference would be the light blue curve, which is the bare copper. That would be an ideal situation. And then the other blue curves is OSP, organic solderability preservative, and then also immersion silver. And basically those two finishes really do not make a difference with insertion loss, or nothing significant anyway. And then immersion tin, the green curve, you can see that does add to the insertion loss. And what's interesting is the immersion tin is less conductive than nickel and gold. So you would think by conductivity, the immersion tin should be the worst, but it's actually not. It's anything with the nickel, any pig or ENIG, they are worse in losses. And that's because the nickel does have, of course, not as good as conductivity as copper, but also the nickel has losses associated with its ferromagnetic properties. Now I want to talk about some process variations that can happen in making circuits and how that can affect RF performance related to final plated finishes. And here I'm showing an example of a microstrip transmission line circuit. I'm using a differential length method. And I have three curves here. One is a bare copper circuit, and that's the blue curve. And the other two curves are using ENIG, electrous nickel immersion gold. But in this case, I asked the circuit fabricator to plate the nickel purposely on the thin side of the normal specification, and that's the orange curve. And then I asked the fabricator to plate nickel on the thick side of the nickel thickness specification. That's the gray curve. So you can see between the thin nickel plating and the thick nickel plating, orange versus gray curve, there's a pretty significant difference in losses, especially out at millimeter wave frequencies. So this normal variation of nickel is something that the designer should keep in mind, and they should work closely with the fabricator to understand what to expect for that kind of variation. Now that's microstrip, and I said before and showed before that grounded coplanar waveguide is going to react even more so, and that's exactly what this curve is showing. Again, it's the same material as the last study that I showed, 5 mil thick RL3003 with rolled copper. And now you can see the difference between bare copper and the ENIG is more dramatic. So the ENIG losses are more. By the way, the y-axis scale is a larger numbers here than the previous slide. So there are more losses here associated with ENIG. But also there's bigger differences between the thin nickel and the thick nickel. So the normal nickel thickness variation in making a circuit is going to be much more significant with a tightly coupled grounded coplanar waveguide than it will a microstrip. And just for reference, the thick nickel, in this case, for the grounded coplanar waveguide, the green curve, at 80 gigahertz, I'm getting about 2.75 dB per inch loss, whereas the previous slide with microstrip, I was getting 1.8 dB per inch loss. So there's a pretty big difference between grounded coplanar waveguide and microstrip when it comes to losses due to this finish, ENIG. So this is looking now at Immersion Tin, same kind of study I've done on the previous slides, except we're looking at Immersion Tin now. The bare copper curve is the cyan or light blue curve, and then the other curves are thin and thick Immersion Tin. And there's not much difference between the thin Immersion Tin green curve and the thick Immersion Tin dark blue curve. There is a little difference, but not a huge difference. And the reason why probably is because Immersion Tin is plated very thin to begin with. Unfortunately, I don't have the numbers with me right now, but it is a very thin coating. So whenever you go from thick Immersion Tin to thin Immersion Tin, it's really not that big a difference in thickness. And I think that's why you don't see a big dramatic change here. Something else to consider is the phase response of final plated finishes. And the y-axis in this case is the extracted dielectric constant using the microstrip differential phase length method. Again, I'm using the 5 mil thick RL3003 materials with rolled copper. And the test method is such that I will make a transmission line, microstrip transmission lines, 50 ohms, and they're identical in every way, except I'll have one circuit that's short in length, another one that's long in length. And then from that, I can measure the phase angle, get the effective dielectric constant, and then do some other things to get the extracted dielectric constant. And that's what's shown on the y-axis. X-axis is frequency. And in this case, I'm showing a very wide band response. I'm going from 10 megahertz all the way up to 100 gigahertz. And you can see how this responds. So I know that the different plated finishes do impact the phase response. And in this case, the phase response was used to determine the values on the y-axis, which is the extracted dielectric constant. So the gray curve is the bare copper circuit. The blue curve in this case is the thin nickel, and orange curve is thick nickel, again using ENIG. So you can see that there's a difference between the bare copper curve and the thin nickel of about 0.1 for the extracted dielectric constant. And that's a pretty big difference for dielectric constant difference. And this is out at, let's say, 77 gigahertz is where this material is used a heck of a lot for automotive radar. And at that frequency, I do see that kind of a difference, about 0.1 difference in the extracted DK at 77 gigahertz between bare copper and ENIG. But the difference between the thin nickel and the thick nickel is also a pretty good difference. It's about 0.05 difference in dielectric constant. And again, at that high frequency and with some of these applications that are very sensitive to DK shift or phase shift, that can be something that's pretty important. So I would encourage the designer to talk to the circuit fabricator and really understand these issues the best they can, and then do some kind of modeling and simulations to see if this variation does cause a problem or not cause a problem. And then one other comment I want to talk about final plated finishes that I run into a pretty good amount, and that is test methods. So we have a lot of customers that will do evaluation on our materials, and one of the more common one is using a microstrip ring resonator. And those are thought to be pretty good for test vehicles for a lot of different reasons. And that's true at lower frequency, but when you get to millimeter wave frequencies, then the microstrip ring resonators have a lot of variables that really need to be considered. And I've got another entire presentation on that if anyone is interested. But here what I'm showing is the effects of nickel thickness only. And I did that by starting off with the same sheet of material, cutting it in half, and then having both circuits, having all the circuits made on the two half panels at the exact same time, same everything, the exact same designs, everything was the same. The only difference was when I got to the point of plated finish, I had one of the half panels plated with thin nickel and the other half panel plated with thick nickel. And again, you can see there's a pretty good difference in center frequency. And as you extract that, that equates to about a difference of 0.023 in dielectric constant. When testing the exact same material, same design, same everything, the only difference is thin nickel on the left, thick nickel on the right. And what happens is that difference in nickel makes a difference in the capacitance in the gap coupled area. So this particular ring resonator had feed lines on the left and right of the ring itself, and then gaps between the feed lines and the ring. And that gap coupled area does influence the center resonance frequency. And in this case, the difference in nickel thickness actually altered that center frequency, which caused an erroneous dielectric constant to show a difference of 0.023 between these two different ring resonators, when in reality, they should have the same dielectric constant. So that's one of those things that need to be kept in mind. And again, I have a lot more information on test methods. If anyone's interested, please contact me and I'll try to do what I can to help. So that's all I have for today, and I would like to invite you to become a member of our Technology Support Hub. This is a website we're really proud of. We have a lot of good information here. You have access as a member to have calculators, free software you can download. You have the Raj mobile app. Also, a lot of technical papers are on here. We have a video library, and we also have a way that you can contact an engineer in your area and ask questions. So with that, I'll thank you for your attention and have a good day.